Alright, hello and welcome to the final review. Oh, it looks like there's a dot there. Let me get rid of that. Yeah, let's review as much as we can for the final. I, of course, can't go over every little thing, but I will give you the best bang for your buck right now. So let's get started. Let's first talk about induction and recursion. And the way we motivated this and got to where we needed to go was all determined by sequences, right? So let's talk about some different kinds of sequences, just to remember all the notation. So you can have an arithmetic sequence if you have some starting value, and then you keep on increasing it by a common difference. So like this is plus 4 to get to there. 4, 8, 12, 16, 20. That would be an arithmetic sequence, and it could be finite, like that could be the last value, or it could be infinite. Whenever you want it to stop, or never, that's fine. So this would be like the sequence value number 0, element 0, S1, S2, and this would be a sequence called S. This would be S3, element 3, dot, dot, dot. So yeah, the way to make an arithmetic sequence is to have a stopping point and to always just add the same amount. That's your common difference, that D, if you remember from the original slides, just to get from there to there. That's what you got to do. Geometric sequences are very similar, right? You start with a starting value, and instead of adding, you multiply by a common factor this time. So like here's a sequence representing the powers of 2, and I skipped one already. 2, 4, 8, 16, 32, and it can be an infinite sequence. And again, the way to get from one to the next is always like times 2, times 2. Yeah, that's a geometric sequence. And then you have a bunch of adjectives that describe sequences. So a sequence can be decreasing. That means the next value is always getting smaller, strictly smaller, 2, 1. That's a decreasing sequence. A non-increasing sequence kind of relaxes that a little bit. It can, it's like it goes in the downward direction, but it can stair step a little bit. Like it can stay at a value. It can stutter a little bit. So it can be like 5, 5, 4, 4, 3, 2, 1. So it's allowed to stay there. It's not increasing, but it's not strictly decreasing either. So we call that non-increasing. And then non-decreasing, these are hard to keep straight in your head, that just means it's not decreasing, but it's not strictly getting bigger. It's a stair step in the upwards direction. So you can stay 1 for a while, stay 1 for a long while, then 2, 2, 2, 3, 4, 5. That's a non-decreasing sequence. It's staying the same or getting bigger. And then finally, an increasing sequence is always strictly getting larger. 1, 2, 3, 4, 5. And these are all finite sequences, but you could obviously figure out a rule to make these infinite as well. And yeah, you can of course define sequences mathematically. This is the sequence A, defined for every n value, for every index greater than or equal to 1. Here is its value for that index. So you can use formulas to write down what's in a sequence, like what's element A1, A2, A3, A4, A5, A6. So let's figure this one out, and maybe that'll tell us, is it decreasing, non-increasing, etc. So yeah, an is n squared minus 4n, so this one's going to be, a1 is 1 squared minus 4 times 1, so 1 minus 4, negative 3. a2 is 2 squared minus 4 times 2, so that's 4 minus 8, negative 4. a3 is 3 squared, so 9 minus 4 times 3, so 9 minus 12, that's 3, negative 3. A4 is 4 squared, so 16 minus 4 times 4, 16 minus 16, okay, that's 0. And then A5, 25 minus 20, that's 5. And then we got 36 minus 24, so that's 12. 12, yeah. Cool, and it goes on forever. This could be an infinite sequence, right? It's defined for every n index greater than or equal to 1. And yeah, this is what it looks like. Is it any of these? I don't think so, because look at how it's going. It's going down, right? Negative 3 to negative 4. And it goes right back to negative 3. That's not allowed for any of these. So it's just none of the above. Interesting. But that's a valid sequence. It's like it's essentially the graph of a parabola almost. That's why it's going down and up. Yeah. So that is that. let's next get to recurrences. This is getting closer to recursion and then therefore closer to induction. So you can define the Fibonacci sequence using a recurrence relation. Remember that? That's where you give some starting values, like Fibonacci sequence, let's call it F. The 0th index, the 0th element of the Fibonacci sequence is 0, and element number 1 is 1. And then after you've given these two starting points, then for f of n, where n is greater than or equal to 2, that value, f of n, is equal to f of n minus 1 plus f of n minus 2. It's always the two previous ones. Remember that? So that's, now this just works off forever, and it's like it's a recurrence relation. It's kind of a recursive definition. Like you'd program this with a recursive function if you wanted to stay true to this. Or a loop if you wanted to go in reverse. Yeah, what about this one? What are the first 6 terms of this sequence? So let's figure this one out. So this is given using a recurrence relation, okay? And so we've got some multiplication going on. By the way, you can define arithmetic and geometric sequences using recurrence relations. Just, you got to give a starting value, and then like the formula involves like plussing the common difference or multiplying by the common factor. But let's do this one. So the first 6 terms of this sequence, C. So C1, C2 are given to us. Those are easy. And then C3, C4, and C5. And then also C6. We'll figure it out. Alright, so C1, that's 4. Give me a second. My cat is right underneath my chair. I don't want to hurt him. There he goes. Alright, C1 is 4, C2 is 5, and then the rest of these are defined like this. Okay, C3 is defined using C2 and C1, right? N minus 1 when it's 3 is 2, and minus 2 when it's 3 is 1. So it's those two. It's essentially saying the next element is the two previous elements multiplied together. So this one's going to be 20. Okay, let me move my cat for real this time. He's in a bad spot. There he goes. Alright. Yeah, so then C4 would then be the multiplication of C2 and C3. So that's 20 times 5, that's 100. And then this is getting large very quickly. So this is C5 is 20 times 100, so that's, 2,000. And then C6, oh no, that's 2,000 times 100. So you start with 2,000 and then add 2 more zeros, so 200,000. And then this would go on forever. So there's their first 6 terms, and this is a compact way of writing an infinite sequence, right? Just always like this is how you build the next term. So you can make that happen with a loop or with recursion. All right, let's talk about summations next. So here's a fun, silly example. Amazon man, Jeff Bezos, I forget how you pronounce his name, but he makes a lot of money. I looked up this like a couple years ago. This is probably larger now, but he makes this much per second, $3,715 per second. So let's use a summation to like represent how much money this guy makes in a day. So remember what a summation looks like. It's like a mathematical for loop. You have a starting index, and you go up to some value, and then you give a formula here for what to do every time you use a new value for your index variable. And so you're just adding all these things together as that variable ranges from the starting value to the ending value. Okay? So how much money does Jeff Bezos make in a day? It's the sum of, well, we want to sum together a bunch of these, right? 3,715. We want to sum this together a bunch of times, as many times as there are seconds in a day. So let's start an iteration variable. It's like this is the first second of the day, and then all the way up to however many seconds in a day there are, which is, let's see, 60 times 60 seconds per minute times 24 minutes, 60 seconds per minute times 60 minutes per hour times 24 hours per day. There. So the answer can be compactly represented like this. That's how much money that dude makes in a day, which is way too much. Hopefully he gives us some. So yeah, that's our summation example. Let's do another one that's slightly more interesting. Let's represent the sum of the first n elements that look like this. So the first one is 2 times 13, then 3 times 23, then 4 times 33. So do you kind of see how these are working? Like what would the next one be? It would be 5 times 43, yeah? And then 6 times 53. See, See the pattern there? So it's always like getting bigger by 10 on the right side, and then on the left side it's getting bigger by 1. And so let's come up with a formula for this. Like this could be our I variable. It could start at 1. When I is 1, we do that, all the way up to like, well, that's 1, 2, 3, 4. Like if I is 5, we'd end up here. So let's make a formula that when I is these things, like it corresponds. So like we'd like to make a summation that sums up the first n elements. Let me draw my prettiest capital sigma here. That starts when I is 1 all the way up to n, right? We want the first n elements. Or this one's totally the first one. So how can we use I equals 1 to get this, and like I equals 5 to get this? What's the pattern? Well, if I is 1 and I want 2, and I is 5 and I want 6, the pattern goes, well, I should start with I plus 1 on the left. And I'll multiply that by something. It looks like this is 13, this is 53 when I is 5, so it's always like I times 10, right? Because that'll get me to 10 here and 50 here, and it's always plus 3 after that. I times 10 plus 3. You see how that's going to be your formula there? And so that can be your summation that just succinctly represents this sum, this idea of doing this stuff. Okay. Next we have induction. So yeah, this is where we've been working towards. So induction is all about you're proving a for all, right? At the end of the day, you are proving this, essentially. For all n in the natural numbers, for every natural number, p of n is true. So you're proving every single p. P of 0, p of 1, p of 2, all of them. That's what induction gives you. It's essentially a way to do a for all proof. For all something, this is true, all right? And then the way to get there, the way that you use induction, is you just use two things. You give two things, and somehow that proves an infinite amount of things, which is nice. It starts with a base case that kicks off everything, like p of 0. That's my first concrete thing that I have. And then the inductive step is where you prove this. You prove that, okay, you prove for all k, you give me p of k, and I'll give you p of k plus 1. P of k implies p of k plus 1. Okay, so this is the kind of proof that you give. So you it's essentially a direct proof after you assume k is an arbitrary natural number or something. See that? And so, yeah, it's really just assume this, assume that p of k is true, use that as firepower to prove that p of k plus 1 is true. And then both of these taken together, you can like build them up. You can build up any answer you need, okay? And this is called your inductive hypothesis, because you are just doing a direct proof at the end of the day. So you are assuming this in your inductive step, and that's so important. We've given it its own little name. It's not just your hypothesis, it's your inductive hypothesis, because you're using that in your inductive step to do induction, okay? So yeah, let's do, just for fun, just to remember everything, let's do the classic proof that the sum of the first n numbers is equal to this closed form. It's equal to n plus 1 times n over 2. Okay, so what's our proof? It's going to be by induction, we say. By induction. If you want to be very specific. And then we give a base case and an inductive step. So we have to figure out, what is our base case? Are you adding up all the numbers from 1 to 0? Like, is 0 the first value that n makes sense for? I don't think so. I think it's more like 1. Like, sum up all the numbers from 1 to 1. So just 1. Okay? So base case should be like p of 1. And this is p, right? P of n. So the sum, all right, for p of 1, the sum of all the numbers, right? Let's use a summation for that. Sum of all the numbers from 1 to 1, column I. See how that'll work from 1 to n, right? That's like your generic proof statement. We're going from 1 to 1 in the base case. And that's just 1, right? The sum of all the numbers from 1 to 1 is 1. We have to show that this right side holds to the closed form still works. We got to show that that's equal to 1 plus 1, which is 2, times 1 over 2. And of course, that is equal to 1, and that base case checks out. And now we'll do the inductive step. All right, so the inductive step is assume this works for k, and then prove that it works for k plus 1. So inductive step. We would like to assume p of k is true, and use that to show that p of k plus 1 is true. Let me draw a better k there. There we go. So assume p of k, and that's just the sum of the first k numbers is equal to k plus 1 times k over 2. So that's 1 plus 2 plus dot 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 all the way to k. That's equal to this closed form where you replace n with k. So k plus 1 times just k over 2, and we're going to use that. What we need to show is this. That's p of k plus 1, right? P of k plus 1 is what we want to show. Show that we can use that to get this. And that's equal to, well, just take this and fill it in with k plus 1. So we got 1 plus 2 plus dot 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 plus k plus 1, right? All the way up to k plus 1. That's equal to this closed form. That's equal to k plus 1 plus 1. So k plus 2 times k plus 1 over 2. That's what we need to show now. Okay, so the trick is breaking this down. Like, we want to use this inductive hypothesis somewhere, so we'd like to be able to replace this with this. That would be helpful. Do you see that that is there? That's your secret. There is that first bit of the sequence just sitting right there, and the only thing that's left is that k plus 1. So let's use that to our advantage. That's how you use the previous proof to get the next one. That's what induction is all about. So all right, here's our proof. So the sum of all these numbers, we need this on the left, right? And we want to end up with this on the right. So 1 plus 2 plus all the way plus k plus k plus 1. That's what we start with. Let's take these guys, right? That's equal to, by the inductive hypothesis, that is all equal to, I'll replace this with what we know it's equal to, right? Because this little bit here, that's equal to this. That's equal to k plus 1 by the inductive hypothesis. I get to assume that that first bit is equal to k plus 1 times k over 2. And then I still have my plus k plus 1 over here. Plus k plus 1. And now I got to get this looking like this. All right, so let's take a common denominator here. I guess over 2 is the right one. So this is equal to k plus 1 times k over 2 plus k plus 1 over 2 times 2 now, right? Because we want it to be the same. And now we have a common denominator. We can bring everybody over and then also multiply this out as k squared plus k. Plus all these guys, plus 2k plus 2. All that over 2. And, okay, that's equal to k squared plus 3k plus 2. And you can factor that, right? You can factor that into exactly what we need it to be. That factors into k plus 2 times k plus 1 over 2. You can check that yourself to confirm. But that's what we needed to do. Bam, QED. And so the base case plus this inductive step just kicks it off forever. And that just shows that for every n, this will always work, which is quite nice. All right, let's see. Keep on trucking now. So you can, before we get to recursion, you can define things recursively, recursive sets. So here's an example that's kind of like a problem I gave you in your homework. Let's define this set here. Let's define a set of strings over this alphabet, A and B. So those are the two letters that you can use to build up your strings, build in your strings, in addition to the empty string, of course. So here is the base case, the basis of our recursive set definition. The empty string, that's going to be part of this set S we're trying to build recursively. And then also just the single character B is in S. Okay? It's like we're building up S the set, and it's equal to some weird blob, and we're adding more stuff every time. It's an infinite set. But the first things in it are lambda and then B. All right, so those are all there. So the two things that we have there to begin with. And then, here's our recursive rule. If we have something in S, then we also must have that thing with an A at the end. That's an S. Okay, so you can add an A at the end. We know that's there. That should be an S. And then also, if you have something in S, that thing plus AB at the end should also be an S. Okay, so our goal is to, this is an infinite set after all, but let's list all the strings of size at least 3, or sorry, at most 3, all the way up to 3 in S. Okay, so let's do that. And so we're going to run this rule a bunch of times, and we'll figure it out together. So, okay. Lambda is an S. The empty string is an S. So it can be one of these x's. X could be lambda. And so I can run this rule with lambda. We know that lambda A then is an S. And we know that lambda AB is an S. Does that make sense? And of course, the lambda is the empty string. When you concatenate that with anything that's real, it just goes away. So this is really the string A. This is really the string AB. It simplifies. So this is the string. We have now A, we have AB in S, and now I can run these rules on all these other things. So I ran it on lambda. I can't run it again and get anything new, but I can run it on B now. Let's run this on B. So I have, I know that I have BA now, right? BA is an S, and then also BAB. BA, BAB, that gave me those. Does that make sense there? It's like the lambda gave me those guys, the B gave me those guys, and then let's use the A now. What do we have thanks to the A? We've got, well, X could be A. So we have AA, and then we have AAB. AA, AAB, so the A gave me these guys. And now I can probably just, let me stop drawing arrows, there's way too much going on now. So, alright, I use the A, let's do the AB. So that means ABA is in S, and ABAB is in S. ABA, ABAB is in S. So that was thanks to this one. That was, these guys gave me that one. I lied. I'll use dashes for a little while longer, maybe. And then we got, let's see, and we don't want to write it multiple times, too. So hopefully I haven't done that yet. And then BA, that's also in S. Well, let's deal with that. That's going to give us BAA and BAAB. BAA, BAAB, and that's thanks to this guy. And if you look at the rule, you will see that it's always going to add one character to the end of something that's already there. So the only new thing that I could possibly get that is under three or more, at most 3, is from this AA. Do you see that? Any of these other ones after that, like the BAB, using this rule on BAB, would at the very least make a string of length 4. And so that's kind of useless to this problem. So let's use the AA one last time and see what it will get for us. So we got AAA, 3 A's total, because AA could be X. So we plug it into this guy. So that gives us AAA, and then AAAB, and I don't think I duplicated anything. I hope I didn't. And then the rest of these, so the AA gave me these guys. Woo, thank you, AA. And then everybody else that I haven't talked about, like this guy, all the length 3 or more strings. If I ran the rule on them, they'd give me longer strings, and I want only up to 3, up to length 3. So I can stop now. There are more in this set. There are plenty more in this set. It's an infinite set. But as far as this answer is concerned, I'm done. Okay? So now we can count them. So apparently we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 strings of length at most 3 in S. So there I am counting them. Alright? So yeah, apparently the 11 is the answer for the number of them, but we're listing them all, so I underlined them there. Alright? I hope that makes sense. So yeah, that's recursive set definitions, and then of course we get to recursive algorithms. So now we can define things in terms of themselves, and then prove that they're correct inductively, which is nice. So yeah, let's do the classic example of factorial, right? Let's solve for the recursion for factorial. If you write enough examples, you'll notice that like here's your recursive algorithm for factorial, right? Just like the base case is 0 factorial defined to be 1 mathematically, and then if anybody asks you for n factorial, that's equal to n times n minus 1 factorial. So it's defined in terms of itself, and then we can go and code that up. We can translate that to code, not too hard. Put it over here. It's like int fact, int n. And, well, it's like, are you in the base case or are you in the recursive case? So it's, alright, if n is 0, return the answer for the fact of 0. Let's just return 1. And then otherwise, return, Well, Rn times n minus 1 factorial. But I can't do it in math. I have to do it by calling ourselves, right? Because it's handing off our smaller problem to ourselves, and it really will work. We can prove that with induction too, that it really will work. This really will compute, this recursive call right here really will compute the smaller factorial as long as everything else is right. Okay? So before we prove it correct using induction, let's talk about recurrence relations. Let's build one for the number of operations that factorial is going to do. Let's find a recurrence relation, T of n, for the number of operations for an input of size n. Okay? So T of n, and that just means look at the recursive case usually. Like, what's going to happen? How many steps are there? It's the time number, I guess, T for time. Timing analysis. T of n would be, all right, how many steps are we doing when we run fact on something of size n, so not the base case? We are going to do, let's see, what should we do? Well, it's going to do a multiplication, and then it's going to do a recursive call. Okay, and that's going to return something. So it's like a couple basic operations, right? A multiplication, a return, that's like a couple things. And then we're also handing off the problem to ourselves, so t again, on a smaller input size, n minus 1. So do you see how the recurrence relation is, well, all right, the time it takes to run it on the sized n problem is, well, the time it takes to run it on the size n minus 1 problem, because we're handing it off to ourselves, plus the extra work we need to do once we get this answer back. We have to multiply by our n and then return, so it's just a constant amount of extra work. So plus theta of n, or sorry, theta of 1 work after that's all done. So this is from the recursive call. And then this is from the extra work, like the multiplication, the returning, all the extra stuff we need to do. Okay? So that's the secret. And we can solve it with a tree, like just like t of 1 is 1 or t of 0 is 1. It'll eventually stop. Like you can say, all right, what's t of n? Let's solve this. Well, it's equal to, well, constant work at this level plus however much work it takes at the level below it, t of n minus 1. And, well, how much work are we doing here at t of n minus 1? Well, you're just running this all over again. Well, we're doing some constant work once we get the answer back, but we're also handing off the problem to t of n minus 2. See that? And then again, that's like handing off the problem to t of n minus 3. It takes that much time, plus some constant work once it gets the answer back. And eventually it'll make its way all the way down to t of 0, which, just like if n is 0, just give back 1. It's constant work once you get down to the base case. So it really will end up being constant down here. And so, like, what do you keep on adding? It's like this tree is, how wide is it? How tall is it? Let's see. I'm not in a good spot to use my mouse. How about this? Will that work? Mostly. Cool. Let's move this over so I can write on this side of it. So how high is this tree of work that we need to do? If you think about it long enough, it is of size n. Okay, it's size n. And then, what are we doing at each level? Well, it's really the actual concrete work we do at each level is constant work. So it's constant work times n, and so it is a linear time algorithm. So that's one way to think about it, okay? Dun, 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 theta of n. And then sometimes you can do it a little bit faster using the master theorem. Remember the master theorem. That means your problem needs to look like this, though. Does ours look like this? Does our recurrence relation look exactly like this? It does not, sadly, because we don't have a division. We're subtracting 1, not dividing by something, sadly. So the master theorem, unfortunately, does not work for this case. So we are kind of forced to use the tree way of doing it. Oh, shoot. I had it. There it goes. Go over here. So sadly, we can't use the master theorem. But that's okay. We know how to do it the other way. And then now let's prove that this function is correct. It really gives back the factorial for an n using induction. So what do we want to do? We'd like to prove that this function, this fact function in C++, for example, is correct. It really gives back the mathematical factorial. So let's think about it. Like, what is our theorem statement? What are we trying to prove right now? What do we want to tell somebody? What is our theorem? What does it mean to say and to prove that factorial is correct? This function. Well, if you think about it long enough, you're really just trying to prove it for all, right? Because that's what induction does do. Like, it proves it for all for you. For all n inputs greater than or equal to 0, right? Because those are the valid inputs for this factorial function. Then you call fact on that n, it gives you back the right answer. So I want to prove that fact on that n, whatever it gives back really is equal to the true mathematical factorial of n. That's what I want to prove. Does that make sense? And so this would be like your P of n. That's what we're trying to show. Okay, and this is our implementation. Let's copy that onto this slide so that we have it. So we'll be looking at it as we do our proof. That's necessary. So okay, now we know what we need to prove. We're going to prove it with induction, and so we have a base case and an inductive step. Let's see here. We've got base case, P of 0. What do we want to do? We want to show that fact of 0 is equal to 0 factorial. Fact of 0, you call it in code, that really gives you back the mathematical factorial of 0. And, well, all right, you run this code. What does it do? Hits the base case, returns 1, so it's giving you back 1. And then 0 factorial in math really does, the answer is 1. So that checks out. And that's kind of what you think about as you're programming it, too. Like, you're doing induction in your mind to prove to yourself that your recursive code is correct. Inductive step. So now we're going to assume P of k, use it to prove P of k plus 1, because that's what we're supposed to do. All right, so assume P of k is true, which is this with k plugged in for n, fact of k. Assume that that smaller call, if you call fact of k, that really will give you back k factorial, the true mathematical factorial of k. Well, we need to show that fact of k plus 1, right? P of k plus 1 is true. You need to show that if you call fact on a bigger input, fact of k plus 1, that really gives you back k plus 1 factorial. That really works out, okay? And so, we've got to show that the code does the right thing as math expects it to do. And so we wrote it with that in mind. Let's make that happen. So, and we get to assume that the smaller call works. That's what this is saying to us. That's what our inductive hypothesis is giving us. So, all right, what happens? Like, what if we start from this side? What does fact of k plus 1 give you back? It's going to hit the recursive case, right? Because it's definitely not 0. It's going to hit the recursive case and give back this. It's going to give back k plus 1 times fact of k plus 1 minus 1. So it will return k plus 1 times fact of k plus 1 minus 1, which is just fact of k. And now we're in business. So there's my smaller number, and I get to assume using my inductive hypothesis, right? Using my inductive hypothesis. So this arrow is just like looking at the code. Look at the code. And now this part is equal to, by the inductive hypothesis, that's what the code's going to do. Now, fact of k, I'm assuming it really will give back the right thing in my inductive hypothesis. So this I can replace with k factorial. So this is equal to k plus 1 times k factorial. And now, all I need to show is like this, what I have now, is that equal to k plus 1 factorial? And it is. If you think about it long enough, like if you had 4 factorial, right? 4 factorial, that's equal to 4 times 3 times 2 times 1. And you multiply that by the next number up, times 5. Do you see how that would produce 5 factorial for you? So that's my scratch work there. That really is k plus 1 factorial. And so that checks out for our inductive step. And so QED, we did it. Mic drop. We've proved that for every n greater than or equal to 0, factorial of n really does give back the right answer. And so now we have some very good confidence. Like, we don't even need to write tests at this point. It is totally going to work. That's really nice. We've mathematically proved that for every number, it's going to work, which is beautiful. All right. So there's still something to be said of, like, if you think about it long enough, like the factorial of large integers probably doesn't, like, you can't hold it in an int. And so, like, it might overflow. So there's more stuff to worry about. But, like, as far as, like, the computation goes, it really, like, if you had enough space in your ints, it's always going to give back the right answer there. So that's pretty nice. Okay. Let's move on now to graphs. Talk about some graph theory. So plenty of terminology as far as graphs are concerned. You got so many different kinds of graphs. You got directed graphs, undirected graphs. So, like, here is an example directed graph. You have always vertices and edges. With a directed graph, the edges are made up of arrows, and, like, we've got ways to get there. So, like, this is a directed graph. Boop. I don't know, go from here to here, here to here, there to there. You can have these bad boys. You can have a bunch of these if you wanted. And so that's a directed graph with arrows. I can transform that into like an equivalent undirected graph where it's just lines. Like you can move around. Or let's make a slightly different one. Why not? So you can go from there to there in any order. Just like there's a way to get there. There's an edge. So it's like a little kite. Oh, I don't like this line though. It's not straight enough for my purposes. So apparently this is the graph that I made last time. Go there to there. You can have these guys. It's not very common. And this is extra uncommon, but that's okay. You can have that in an undirected graph too. So these are, all right, made of the dots are vertices, right? These are all vertices. Singular is vertex. And then we got edges. These are directed edges. These are undirected edges. We can ask for the degree of both the graph and of a node of a vertex. So the degree is the number of things, like the number of adjacent things. So like the degree of this vertex is 3, the degree of this vertex is 2. You can ask for the degree of the whole graph. Let's see. A subgraph is when you take out a piece of the graph, like you start chopping off edges or vertices. So like here is, if we start with this graph, I can chop off, I can take only these pieces of it. Like that's a piece of that graph. It's a subgraph. It's a graph inside the graph. So you see how this is a subgraph. Like I take only a few edges or only a few vertices, or likewise I chop off only a few vertices or only a few edges. And then we have like parallel edges and self loops. That's what these are. So these are parallel edges. They're edges going from the same two vertices, like going from here to here, but there's like two different ways to get there. There's like a fast route, there's like the toll road, and then just the normal highway or something. And then here's the same thing for undirected graphs, parallel edges and self loops. And, parallel edges, those are parallel edges, and then a self loop looks like this, like you're coming back around on yourself. It's more common in directed graphs than undirected graphs, but technically it's possible there too. It's a little path that you can walk on and go right back to where you started. So yeah. So these terms next are the hardest ones in my mind, at least, to keep straight in my head. It's disgusting. So all right, let's try and talk about them together. Let's talk about walks. All right, so here is, let me expand this as big as I can get it. Slightly better. So a walk is the most generic kind of way to move around a graph. All right, it's when you list out all the vertices that you visit and all the edges that you pass. So like a walk looks like this. Like I can walk back and forth between these edges like 50 times, and that would be a walk. And you'd write down, all right, I started at this vertex, I crossed this edge from V1 to V2, and then I went to V2, and then I followed this next edge, ... So you give that kind of sequence. So that's a walk. It's very generic. It's just like list out all the vertices and the edges you go across. Like here's a walk. I go around here a few times, go back to here, and I go back and forth. I pace back and forth a few times, and I go up here, go over to here. So that's a walk. Okay? Just list out all the vertices and edges that you go across as you move around the graph. It's just arbitrarily moving around the graph. That's a walk. There are no site conditions, no requirements. Okay? So that's your walk. A circuit is a little bit more precise. A circuit is you have a walk, but you're not allowed to visit any edges multiple times. So like, you can't like come back around on yourself. No edge more than once, but you also have to come back to where you started. Okay, so it's a walk where you can't duplicate edges, you can't duplicate vertices, and you have to eventually end up where you started. Okay, so here is a circuit that is not, let's see, let's do a walk first. Like here's a walk, boop, boop, coming straight back. That is not a circuit because I reused that edge. See that? So that was a walk, but not a circuit, but like this would be a circuit. Like I used all those edges and came back to where I started. Or, likewise, this is totally okay. Oh, sorry. No, it's not. Let's see. What can I do to like reuse that parallel edge? That's my goal right now. Let's do something like that. There. Is that where I started? No. Let's start there. Let's start right here. Oh, darn, I have to add some more edges to make that actually work. But like here, this, for example, that's a circuit. That's okay, because I'm not reusing edges, even though I am reusing like vertices a couple times. Like even that, I guess. That's technically a circuit, all right? Not reusing edges. So I hope that makes sense. But like a walk, you can just like pace back and forth and then wrap it around. That's allowed. You can reuse edges all you want. Paths is a little bit more side conditions, more requirements. So that's when you can't visit vertices or edges more than once. So like this for example, that's a path right there. But I can't do this. Like I can't come back, and then also I can't reuse vertices or edges more than once. So I can't follow, like, let's see, I can't like reuse that because I'm coming back to where I started. I can't like go back to here. That's not a path. Okay. The path is you can't use multiple edges or vertices. So like the maximum length of a path in this graph is 3 because you count the edges. And then finally cycle. Cycle is pretty much a path, but you've actually relaxed your side conditions in one way, or maybe there's one last condition. It's a path, but and also the first and last vertices, they get to be the same. So here's a cycle. Boop, like that. All right. But you can't repeat intermediate vertices. So like boop, boop, that's not okay. Okay. So like here, let's say I started here, went to here, and then like went back around and then back. That would not be a path because I reused this vertex. I came back to it. That was not okay. All right. So no edges or vertices used multiple times, but then also you are allowed to come back to where you started. So like this cycle. Oops. This is a cycle. And then I might have messed up when I said path. Like this is not a valid path because you came back to where you started. You duplicated that vertex. Like this is a valid path. This is a valid path. And then if you close it off, then it's a cycle. Okay? Just want to keep that straight. Sorry if I messed up earlier. So I was looking at cycle while I was talking about paths. So that's all that information. These are hard to keep straight in your head, I know. But that's good to learn it so early in your computer science career so you can't mess up later. Let's see, we can also talk about connected, disconnected, connected components. So much fun stuff. So graphs are connected if you can move around, like there's a vertex or there's edges that link all the vertices. So like this, for example, is a connected graph. You can always get to anywhere you need to go. Let's see, this graph, I wouldn't call it connect. I don't know. I'd have to go back to the technical definition of a graph, because like technically if you're here, you can never get back to here. So I forget if that still means it's connected or not. Maybe it only has to do with undirected graphs. So let's just keep it to undirected graphs right now. You can go back into the book and look up if it works for directed ones. But like this graph is totally connected. Some graphs though are not. Some graphs there's no ways to get between places. Like here, maybe all these three things are connected to each other. Here's an example graph, but like this is part of the same graph over here. These guys, there's no way to get from here, from any of these to over to here. See that? So that's a disconnected graph at that point. But when you have a graph that's disconnected, like here's here's more vertices and edges in the graph. Like let's say this is our whole graph right here. It's disconnected, but there are tiny pieces of it that are connected, and those we call connected components. It's like here's a connected component of the graph. Those three vertices, at least, among each other, are able to move around between themselves. They're all connected. Like same with those two vertices and these three vertices. Those are connected components. This graph is disconnected, but it has three connected components, we say. Okay? So let's talk about regular graphs and then some other terms. So a regular graph is when every node has the same degree, all same degree. Okay? So for example, this graph. Everybody's got the same degree. Degree 2, degree 2, degree 2. That's what it means to be a regular graph. They all got the same degree. Then we have cliques, pronounced cliques, and we for short, we write k sub n, where n is the number of nodes. Okay, clique, or kn, let's draw out k4, for example. That's when every node is connected to every other node by an edge. So like here is k4, I've got 4 vertices, and all I need to say is k4, and it describes exactly this graph. So it's like, all right, this vertex, it can go to everybody, and every other vertex can do the same. Like this one can go from here to here, there to there, this one was already here, and like this one. Do you see how all of these can get to everywhere else immediately with one jump? Okay, so that's a clique K4. Technically, also, when you have a clique, it's regular. It's definitely it's a special kind of regular graph, right? Technically, also regular. But we can describe it better by saying it's K4. Technically, also, it's a regular graph because they all have the same degree, right? These all have degree 3. Also regular. That's pretty nice. And then finally we have this KNM thing. And that's like, there's 2 components of it in a sense, but not in the connected components kind of sense. There's two sections of the graph where those pieces are not, they don't have edges between themselves, they only have edges to the other side. All right, so let's draw, for example, K34. That's how you write it. And what it means is, all right, there's a group of 3 vertices over here, 3, and then there's a group of 4 vertices over here. And these individual groups are not, there's no edges between themselves. Like you can't get from here to here, or there to there. Like these edges don't exist. But every possible edge from here to all of these guys exists. That's what it means, all right? So this node can go to all of these. Same with this one. It can go to all the 4 on the right. All right? Or you can think of it from the perspective of the nodes on the right side, like this one can go from here to here and also to there. That's another way to think about it, but they can always get over to each one of them. Boop, 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 and boop. So did I miss one? I missed that one. There, that looks better. So that is K34. So you see how this one has, all these nodes on this side have degree 4, at least they better, yeah. And then all these nodes have degree 3 because they're able to get immediately to any of those ones on that side. So that's that kind of graph. I think that's all that. And then, like, these are nice things, and we like to use graphs for many things, but how we put them inside of a computer, there are 2 standard representations for graphs. You got your adjacency lists and your adjacency matrices. So let's have an example undirected graph here. Let's do this one. You can also use these to represent directed graphs. Let's draw this one, A, B, C, D. Here's my graph, and here are the names of the vertices. And let's say that I have these edges in my graph. Oh, it's not straight enough for me. There we go. That one, and then that one. So an adjacency list it's essentially a map, right? It's a map from node names to lists of all the things that it's adjacent to. So like A, you got an index in your map for all the nodes. Like you got an A index, a B, a C, a D. It's a mapping from all their names to a list of all the things, all the nodes, all the names of nodes that each of those are adjacent to by an edge. So A is adjacent to by this edge B and by this edge C. So I put in some order, doesn't have to be in any special order. I have a linked list over here essentially, like a set. I got BC. Because A is adjacent to those things. That's what we're representing in our adjacency list. And then B, what does it map to? It maps to a list of all the things that B is adjacent to. And that is all of them. All the other guys. A, C, and D. In any order. It doesn't have to be in alphabetical order, but I'll write it in alphabetical order for us right now. So B is adjacent to A, B is adjacent to C, B is adjacent to D. And then what about C? C, from its perspective, it's adjacent to A and B. And so you see how this could be, if this was a directed graph, like you just wouldn't put it in the other side. C is adjacent to A, C is adjacent to B, but not D. And then D, so lonely, it's only adjacent to B. So it would just be a 1-element linked list or something over here. One element vector, 1-element set. You can have any data structure over here. We think about it as a list. That's the minimum thing. Just put a bunch of stuff, all the things it's adjacent to. And so this is nice and compact, especially when there aren't a lot of edges. Like, if it's K4, like, you're going to have a lot of things here. But, like, when there aren't a lot of edges, adjacency lists are nice because you only have to specify the ones that are there. Adjacency matrices, though, do not have that luxury. You have to list out a 1 or a 0 for every pair of vertices. Like, is there an edge between them or is there not? So let's label this in some sort of order. So like A, B, C, D goes in that order. So I'll make a grid, a matrix, and I'll line these bad boys up. And I'll put a 1 in the cell of my little spreadsheet or something that represents the graph. I'll put a 1 if there is an edge between those two things. And I'll put a 0 if there is not. Let's do it row then column. So like this is saying this edge, this piece right here is saying, is B adjacent to A? Is there an edge from B to A in that order? Okay. You can do the other way too if you wanted, but doesn't really matter if this is an undirected graph though. So let's say here, there are no self loops, right? There's nothing from A to A, B to B, C to C, C to D. So there is a 0 in all these bad boys, right, along this diagonal. But it is also mirrored along the diagonal because it's an undirected graph. Because if A is adjacent to B, right, A is adjacent to B, so I'm going to put a 1 there. That also means that B is adjacent to A in that direction, right? B is adjacent to A. It's saying the same thing. So it's like, it's flipped along this axis as well. So B is also adjacent to A. So I'll put a 1 here. All right, so that was that one. A is adjacent to C, so likewise, A is adjacent to C, so I'll put a 1 there. And then also C is adjacent to A, so I'll put a 1 here. And then B and C, so B is adjacent to C, and C is adjacent to B. And then finally, for our fourth and final edge, we got B adjacent to D. There's an edge from B to D. B to D, and then D to B. And then everything else that wasn't specified, there's a 0 there. So you see how you're kind of wasting space because the adjacency list doesn't store the zeros. It's only storing the ones, essentially. But this guy's got to store everything. And so when you have lots of lots of missing edges, then you might want to reach for an adjacency list. And most people prefer the adjacency list way, unless you're doing something special. So yeah, let's for the final bit about graphs, let's talk about Euler things and Hamiltonian things. Remember all of those fun ideas. So Hamiltonian, you can have a Hamiltonian cycle and a Hamiltonian path. And that's when you have a cycle/path that includes every vertex in the graph. So it's talking about vertices. So Hamiltonian stuff is talking about vertices. So like if I have this graph here, boop, there might be a bunch of edges. Might be a bunch of options as well. But like if you're looking for a Hamiltonian path, that's just use the edges in some way to visit every vertex. Can you do that? You can if it's disconnected, right? So there's a million different ways to get a Hamiltonian path or a Hamiltonian cycle. Let's start with path. So like this, for example, is a Hamiltonian path. It's going to every vertex, and it's a path. You could also probably do a stairs, like a Z kind of thing. Boop, boop, boop. That would be fine. That would be a Hamiltonian path. And then some of them you can close off, and you can make Hamiltonian cycles. So this would be our Hamiltonian cycle. I think this might be the only one, in fact, because you got to like come back to where you started, so don't like block your way. Like this would be one. Go around here just in a little loop. So like that one, and then that one, and then that one. So this right now is a path, right? From here to here. That's a Hamiltonian path. Then you can close it off with that one, and that would make it a cycle. Hamiltonian cycle. That includes every vertex in the graph. And then the other one was Euler circuit. So Euler was about every vertex and edge. So it's when you make a circuit that contains every vertex and edge. And so we're not calling it a cycle, right? Because you might have like parallel things. It's okay. Let's do my favorite example from the milk carton when I was in elementary school. Let's see if I can remember it. So here is the graph. We want to find an Euler circuit, a circuit that goes to every vertex and edge in this graph. Let's see. And there's also something in the middle there. There's also a vertex here. And so, boop, these are all here as well. Boop, just like that. There's really a bunch of tiny edges in here. And I'm doing my best. I cannot do the straightest of lines right now. Getting there though. So there's my graph. Let's find an Euler circuit. Circuit containing every vertex and edge. And I know I have to like do one of these weird things. So let's figure it out together. So here, 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 here. Oh yeah. First try. I'm getting good at this. There. So, did you miss it? You can rewind, because I'm not doing that again. So I'll probably forget it. But I think I started here and I went up and then made that thing. I think that's the secret. But yeah, that's an Euler circuit. Contains every vertex and edge. It's okay to come back. Like I had to come back to this guy a lot. And that's good that it was allowed to be a circuit rather than a cycle in that case. Alright, let's look at trees now. Time for trees. So, just a little bit on trees. We know a lot of this from 41, right? So don't have to do too much. We got new things, right? We got trees that have many, like not just binary trees. We got free trees that just like sit around. Like here's an example tree. You can have a free tree. It's just like over here. All it means to be a tree is like you've got a certain number of edges, right? It's like connected. There are no cycles. That's kind of what it means to be a tree. So this is like, it's a graph, but yeah, you can describe it as a tree. This is a free tree, just laying around, there is no root. But then you can also specify, like, this is the root or something, and then it becomes a rooted tree, okay? So you can also have just them sitting around. And yeah, so let's talk about rooted trees as well. You have, like, the idea of a level. So let me draw a rooted tree over here. You can have a lot of, you don't have to have just 2 children, that's a binary tree. You can have like 3 children, that's okay. You have different edges for different things. Let me try to keep these in line actually. Do that one, and maybe this one has that. So if this is our root, let's talk about levels. This top thing is the root. A level is like how far away, how many edges down from the root are you? Like this would be level 0, the root's at level 0. Level 0. And then this would be level 1. Level 1. Level 2. Level 3. That's kind of counting edges again. The height of a tree is the max level that exists in it, so 3 would be the height of that tree. Parents and children, that makes a lot of sense, right? This is the children of this are all these guys. And then likewise, the parents of all of these are the same thing, that node up here. The root is the parent of this node and this node. Ancestors is just like a bit farther, right? The ancestors of this node are this one, its immediate parent, its grandparent, great-grandparent. You get the idea, right? Descendants is in reverse, like everybody's a descendant at the root. This node, what are its descendants? Well, its immediate children, and then their children, and then their children's children, if there are any. So you got all those guys. Leafs are nodes that have, in a rooted tree at least, leaves are nodes that have no children. So like these guys are leaves. In a free tree, a leaf is just anything, any node. Let's pretend for a second there is no root here. In a free tree, your leaves are just any nodes that have degree 1, essentially. Treating it like a graph. Like this would be a leaf in the free tree. This would be a leaf. This would be a leaf. This would be a leaf. Okay? It's like they only have degree 1. So that's that one. And then the idea of a subtree. Like just like cross offs or just pick out certain edges and nodes. They do have to, it has to stay connected. It has to be a tree still though, right? So it's not, you can't just like chop off this one and like keep everybody else because like you lost. Now you have 2 connected components, and it's a graph but not a tree anymore. So you got to keep it a tree. It's like, let's say I take just these guys. This would be a subtree. Okay, that's the idea. That's that. And like you can do a subtree of a free tree as well. Like this could be that guy, just like that. That's just this bit. But you got to keep it a tree. Okay, so there's that. Yeah, let's do traversals real quick. You got a bunch of different kinds of traversals that visit everybody in the tree. You got your pre-order, post-order. So the prefixes here mean in which order do you visit the root, because this is going to be a recursive algorithm. So pre means root first. visit your root, and then recursively visit your children. Then children. And then post order means visit your children recursively first, in some order, then your root. So these are fine. Then root. Then look at the root. And it's okay. That's supposed to be an N there. Then root. And it's okay to do this on like large trees that have multiple children. So let's do it on this exact tree. So just to make it all work out, so we can do in order as well. Let's make it a binary tree. But these do not have to work on binary trees. You could run on any kind of tree. So this is A is the root. This is BC. This is DE. So for pre-order and post-order, let's do those. Do them in green. What's the pre-order traversal on this tree? So you start with the root, right? So it's root, then children. Root, left, right, essentially. So root, left, right, recursively. So root is A, so we're going to look at the A first, and then recursively go down this side, and this guy's waiting. So now we're recursively working on this one. So it's root, left, right, BDE. And then, so that we did root, we recursively did left, now we recursively do right, it's just C. Okay, so that's that order. For post order, it's kind of the opposite in a sense. It's children then root. So, all right, if I'm going to do post order on this entire tree, I need to recursively go down post order the left, post order the right, then I can look at the root. So A's last. Okay, so recursively post order this guy. So it's recursively children, then the root. So DEB. And then, all right, we did, on the whole thing, we did left. Now you go recursively right, and then root. So C, then A. So just like for this little bit, you see that B is last for the subtree as well. It's important to understand. And then in order is for binary trees only, and that means you're visiting the root in the middle. You have to do left, root, right. In that exact order. Left, root, right. All right, so let's do that one. So in order. Oops, I did not mean to click that button. Oh no, now it's loading. Go away. Okay, cool. Let's go back to green. So in order. So it's always left, root, right. And somehow I deleted too much stuff. Right. Okay. So I want to in order this entire tree, so I'm going to recursively in order left, then visit the root, then in order right. Sorry, I'm working on this guy. So again, in order is left, root, right. So DB. So that was left, then root, then right for the original tree. So then A, then C. All right, so everything's a bit different. And then finally, breadth first traversal. Breadth first search, I guess, is the same idea from graphs. But like you start at the root, you use your Q, and it's just going to go in level order. So this way, then this way, then this way, like that. So that one's easy because of the way I labeled things. So your breadth first search kind of traversal is A, B, C, D, E. That's easy to just read off. Okay. And those go hand in hand with your graph traversals. Graph traversals of graphs produce trees. So let's talk about a certain graph. Let me have an example graph. And then we'll talk about depth first search and then breadth first search on each of them. So let's make a graph, and I'll label some nodes. So here's my graph, vertices at least, and let's say these are the edges. So these guys are all like this. And then we can go from here to here, and we can go from here to here. So this is my graph. This is my graph. And I want to do breadth first search and depth first search on it, so I'll just duplicate it twice. So this will be A, let's call this B, just for fun, C, D. We'll go in that order. Oh man, C, D, E. Okay, and let's duplicate that so I can do depth and breadth on it separately. So yeah, depth first search is essentially post order. You can use a stack or you can use recursion. But it's pretty much post order for graphs where you try to go down as far as you can. It's like look at the children essentially of your node, if you can think of it that way. Like look at the adjacent things first and then like get as deep in the graph as you can go. It's essentially post order. So here's DFS. And let's say that we start our depth first search at the A node. All right, so let's do it starting at A. Like A is the first thing we see. And then I would like to, on a stack essentially, I'm going as deep as I can. And let's say whenever I want to make a choice, like right now, A, I have the choice of looking at this edge, going to B or going to E. Let's say I always choose the thing that is lower in the alphabet. So you can draw out the stack, but I'll just do it quickly. Like A is going to look at B. And like I visited A and B at that point. B is the second thing I see. And then B could see I can go to A or I can go to E, but I've already been to A. So I'm going to E next. So let's go in there. And then E is the third thing we see. And then E is like, all right, from its perspective, I'm trying to go as deep as possible. That's depth first search's jobs. Like I can go here, but A has been seen. So I'm kind of forced to go to D now. Boop. That's the fourth thing I've seen. And then same with D. Like I could go this way, but I've already seen E. Or I can go this way and make progress. And then at that point, you've discovered the whole graph. You'll have duplicates in your stack. That's the fifth thing. But they'll just get popped off at that point. So it made a tree. It made like essentially a linked list, but it made a tree, more or less. That was the way it found it. It's a depth first traversal tree. It discovered every node in the graph and it tried to go as deep as possible. All right. Breadth first search is kind of the opposite. It wants to go as wide as possible. And so it uses a queue and just keeps track of things. So let's say that we visit A first. Like A is our root node of our breadth first traversal tree. And it's like, all right, I can go to B and I can go to E, and it's going to do them both. It's going to go here, and it's also going to go here. It's essentially pushing these into a queue. But you can think about it this way. So like B is the second thing that it sees, and E is the third thing that it sees. If we're going to consider it in alphabetical order. So like it's pushing those to the queue. And then like it's B's turn, because it's on the queue next, right? It's in order. So then it's like I can go to A or I can go to E, but oh no, they've already been seen, so I'm good. And then it's E's turn. It's like, all right, I can go to A. I've already been there though, or B. I've already been there, but I could push D, and so it'll discover D through E. It goes there. That's like the fourth thing, and then all those get popped off. And now it's D's turn. I could go to E, but it's been seen, and so it'll just go to C. And you see kind of the difference there. It's trying to go as wide as possible. It's trying to go like this. Boop, 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 boop. It's trying to be as balanced as possible. Like notice nodes and try to get the shortest path to them in terms of edges. That's what breadth first is good for. Depth first is just like head first, going as deep as possible. But breadth first tries to stay close to the surface as long as possible. So that was BFS. Okay? And so I encourage you to draw out the stack, like confirm like this was really right for DFS, draw out the queue, confirm that this was really correct for BFS. But that's as far as I want to go right now, and just to help you recall the things. And so kind of the point of the review always is like to show you stuff. Like I can't show you everything, but I can show you a bunch of words. I can say a bunch of words, draw some examples, and that should help you notice which things you need to hit harder when you're studying yourself. So that's kind of the goal of every review lecture. But that's where I want to stop for now. I will come back and we'll start with counting next. So that's where I will see it in the next lecture.